Hello everyone, this is another Prolog lab, and today I'm going to show you how to implement the tic-tac-toe game in Prolog. So the first thing we will do is we are going to start a new file, and we are going to call it TicTacToe game. Okay, and we are going to start the game. The first thing, I've already done this for you before, but I'm going to explain the steps. The first we are going to do is to make some decisions. Okay, so these decisions are about the encoding. How are we going to encode the board? So one option is to make the board an array. Okay, and the first three elements in the array is the first row on the board, the second set of three is the second row, and so on. So initially, the board is going to contain blanks, 9 blanks, the first row, the second row, and the third row. Okay, the next thing you need to decide is moves, how to encode the moves. Okay, so we already know we can have 1 or 0 for each player. So a move will mean changing a blank symbol from blank into 0 or into 1. Okay, so we have the board, we have the initial position of the board, which is blank. Now we should define winning positions or winning configurations. So for example, a winning configuration can be this: 1, 1, 1, and then you can have anything else on the other. We can put anything there, right? X2, Y2, Z2. I mean, these are variables. So basically, this means that you've got a winning configuration on the first row. And then I put variables for the rest, okay, because you don't care what it is, but you can have anything there. So the winning configurations can be along the row, or they can be along the column, or they can be along the diagonal. So I have already wrote these configurations for you, and I'm going to copy them across. Okay, so these are the configurations. Okay, so I have a predicate called row win. So when there is a win along the row, the board is the array, basically, that represents the board, and the player is a variable which can either take the value 0 or take the value 1. And of course, I don't want to keep writing 1, 1, 1, 0, 0, 0. I just use a variable to say that if the player managed to set his symbols across the row, one next to the other in a row, then he wins. Second row, third row. The same for the column. Okay, so we have the column. Yeah, the first one, which is column 1, column 2, column 3. And then in diagonal. So we have the first diagonal and the second diagonal. Of course, the board is symmetric. So these are the winning configuration. Now you have to put them together and say when there is a winning configuration on the board. So we put them together with this predicate. Yes, so we say the board is a winning configuration for a certain player if the player won on the row. A board is a winning configuration for a player if there is a winning configuration on the column. And the last one, the board is in a winning configuration for the player if there is a win on the diagonal for that player. So this is what we've defined. Now, of course, what you could do is compile and run as it is. Okay, so I'm going to make this one. And let's have a look at our... So what can I do at the moment? What's available for me to do? Well, at the moment I can simply call the predicate row win. So how about we test this predicate? Okay, so what does the row win receive? Well, receive a board and a player So let's make a board to check if it's a winning configuration. So we can do 1, 1, blank, 0, blank, 0, and then 1, 0, 1. And the player, let's say that the player is the one with 1. Of course, this is not a winning board because we don't have a win on the row. Now let's make it a win on the row. So I'm going to make a win on the first row, and of course we are going to get true. Let's now do column win. So column win should return false. There's no win on the column, but we can make it win on the column. So what I'm going to do is, for example, I mean, here you can have anything, right? Let's make a 1 here. Oops, sorry, we have all this other stuff from the previous. So let's copy column win. So we have column win. We can make column win by simply putting 1, 0 here, right? So let's make it 0. So 0, 0, right, on the second row. And we have to have another 0 here to make it win on the column. Let's have a look. Column win. Oh yeah, for the player with 0. That's true. Excellent. So we have defined some of the predicates. Now this is not really playing the game at the moment. So what do we need to define now? So we've defined the configuration of the board. We've defined the winning positions. We need to define moves. How do you move? And we said that the way we move is by moving one position at a time. So at each position, we change a blank into a specific symbol. So let's define the moves. So I'm going to copy them. Okay, maybe I should copy the first one so you can see. Okay, so in this example, what am I saying? I have a predicate called move. The first parameter is the board. The second is the player, which can be a symbol. And then the third is the actual output. How does the board change? So you can see in this situation, the board has a blank on the first corner, right, topmost left corner. And what happens here? I replace the blank with the player. Okay, so the player is moving on that position. Now you have to do this for all the other positions. So therefore, I have other predicates. Now you're going to say, well, how many predicates do I need? Well, you need 9, right? Because you've got 9 individual positions. So you can see here how he's moving on the second position, the third, the fourth, the fifth, the sixth, the seventh, the eighth, and the ninth. So we have defined a move. Let's try and compile. And I'm going to call the predicate move. What do we need? Well, we need the board. So let's just take this board configuration. Okay. Or maybe you want me to make a simple one. Okay. So we have this board configuration. I want to give the player, so who moves? Okay. Let's make the last ones blank, just to make it easier for us, right? So blank, blank, blank. Okay, so we have 2 1s, 2 0s. So let's say the player with the 1 moves. And of course, you can see here that the moves are done in order. So we know that the next blank, or the blank that's to be replaced, is actually the first blank in the board, on the board. It's done in order, not randomly. Okay, so here I'm going to move. So what's the new board? So new board is a variable. So let's see what it gives us. And you can see that exactly that happened, that the first blank was replaced with a 1. Okay, so these are the moves that we defined. Let's go back. So we've defined the board, we defined the winning configurations, we defined the moves, and now let's do something that prints nicely. Okay, so I'm going to have a predicate that prints the board. So, you know, we can have a nice way of seeing the board printed. Okay, so let's go to here. Print board takes only one predicate, yeah? I'm going to clear the screen. So we do print board. Okay, print board. I hope I remember the exact print board. Excellent. Okay, and full stop at the end. And you can see the board has been printed. And of course, if we want to make the move, okay, so we say move onto the board, and then we can print the new board. Okay, then we can see the new board has been printed. Okay, so it's moved replaced the first blank on the first row with a 1. Okay, so we have the printing of the board. The other thing you need is to alternate. So what happens is when the player with 0 moved, you need to switch the symbol to a 1 for the other player to move. So this is done by this predicate, okay, which changes the player. So if, okay, this is X and 0 instead of 1 and 0 that I have. Okay, so X and 0. If it's X, then we move to 0. If it's 0, we move to X. So now what we need to do is to define the playing. Okay, and this is done recursively. Now one thing to know is that Prolog is a recursive programming language, and it already has an inbuilt mechanism that searches recursively. Okay, so how do we play? Well, we have a predicate called game. It receives a variable called board and the player who moves. What is the stop condition? Well, the stop condition is we check if we have a winning board. So after a player makes a move, we check, is this a winning board, the one we are looking at? And if it is, we stop and we write a message saying that the player, and the player is a variable, right, with capital P, will print either X or a 0. And we say that the player won. What do we do in other circumstances when the board is not a winning configuration? If it's not a winning configuration, what do we have to do? We have to switch the player, okay, make the player move, okay, and check again. So this is what is done in here, okay. Right, so what we are saying, if the board is not a winning configuration, this is the stop condition. Now we have the if statement. Then change the player. So we use the predicate other. So we switch the symbol, and then we make that person make a move. But now question, what if there is what if there's a tie? Okay, because one thing we haven't defined on our board is a tie configuration, because there are so many, right? So you can't really define tie configuration easily. So we need to account for that. So what we say that if you can't move, now if you can't move, this particular predicate will return false. So let's have a look that that's indeed the case. So I'm going to fill everything up, but I'm going to make the x's, right? Because remember that we have x. So let's say that we have 0, x, 0, x, 0, and then we need 3 more. 0, x, 0. Okay, so we have first row, second row, and third row. So imagine that now the player with x is supposed to move. Now what should happen, right, is that we should get a false. Okay, I'm going to remove the print at the end there because we don't want to print. So really, we should really return a false because there's no way in which we can move. The board is full. So this is what we are accounting for in this code. If we can't move, so this returns false, then you stop. This is what this cut tells us. Okay, now I'm going to talk to you about the cut later on, but simply what you should be imagining is that Prolog generates a tree, and the tree is a search tree, and is done by simple